Welcome, everyone. Today we have Eden from Classiq back with us again for the fourth session in the series of advanced quantum algorithms and implementing quantum primitives over Classiq. And yeah, over to you, Eden. Please take it away.
Great, thank you. Cool. So today's the fourth. Wait, I think a technical thing. I think the video should be pinned. Can you see me in the video? Yeah, perfect. Great. So today is the fourth and last session of the first part of the training, and I think it's a really nice and interesting session because I will cover a new aspect of the quantum primitives and advanced quantum algorithm, and it's more on a way of thinking. And so we will have two parts of today's lecture. So the coming 1 hour will be on the implementation of advanced quantum algorithms. And then the second part, one of our co-founders and the chief product officer, Amir, will come and give a more overview of the Classiq Git library and how many implementations of advanced quantum algorithm are aggregated over there. So what you'll gain by the end of today's session, the main thing that I want you to go out with is a way of thinking about how to implement quantum algorithms from papers in practice. So I think it's a different thing, or one thing to understand a paper or understand a quantum algorithm on paper, and it's a totally different thing to have the ability and to actually being able to code it, to design it, and then to implement it. So as I've said throughout the course so far, when we are coming to implement something, we really need to understand it deeply, and then there are many nuances we need to face, and I think this boosts our understanding even more. So this is what I want you to go out today. It's a way of thinking how to implement quantum algorithms from papers to advanced algorithms in practice. So in the first hour, as I said, we'll go through the implementation, and the example we'll cover is of quantum walks. So a very short theory. We won't cover the theory or the broad understanding. And I think some of the participants in the audience have more background and know more about quantum walks, about the theoretical parts of it than I am. And then the second part will be decomposing into the encoding and the evolution. So as we've covered in previous sessions, we divided the quantum algorithm framework in general into three steps. So first we have encoding of the data, then we have the evolution that we want to do it in a smart way, and then we need to do a measurement, and we want to post-process the results. So today we'll decompose only to the first two steps, and we'll ignore the third step for now, and then we'll go through the full implementation. So this will be the first 1 hour, and then we have a short break, and then Amir will come and introduce the Classiq Git library, which contains many implementations of advanced quantum algorithms. So a brief introduction of quantum walks, or just to state what it is. So it's a framework of quantum algorithms. It originated the idea come from classical random walks, and then there was a quantized version of quantum walks. And from the first version, there were many different things that are called quantum walks. And at the end, I'll give you some references where you can view a good tutorial or a good review of the entire quantum walk material. It has applications for optimization and for graph analysis and for many other applications that other also quantum computing algorithms, quantum algorithm give some application for. And the scope of today is discrete time quantum walks. So on the high level, there are two types of quantum walks. So one is continuous time quantum walks, and the second is discrete time quantum walks. And today we'll focus on the discrete time version. Even within the discrete time, there are a few different methods or a few different sub-frameworks that usually are used. And today we'll use one of them. And again, there is at the end, I'll give you a proper review that you can have the high-level view of all the quantum walks available, or all the frameworks and the sub-frameworks. Today, we won't discuss the theory. So we'll actually go from a short paper, actually a lecture notes of advanced quantum algorithm, but one of the key speakers that will come later on. But we won't discuss the theory. So we'll just go through the paper and understand what are the key components and how we can implement them, and go through the mapping from the paper to the implementation quite thoroughly, but we won't discuss the high-level theory today. And this is the review that I told you that you can search later on, and then you'll have a more general overview. And I think some of the participants can share also further reviews that maybe they've written or they encountered. For this is an active area of research, so there are many reviews out there available. So what is the setting that we have when we talk about quantum walks? So we have a classical graph. What I mean a classical graph? We have nodes or vertices. We'll mark them as V. So the set of all nodes or vertices is denoted by V. And we have the edges. So it's connected vertices. So the lines that connect the vertices. This is an example. So this is a graph. What we have here, we have 4 nodes. So we mark them by the numbers 0, 1, 2, and 3. And the set of the vertices, so V, is the set of the available nodes that we have. So it's 0, 1, 2, and 3. So this is the set of the vertices. And the set of the edges are all the tuples that are with 2 connected vertices. So we have 0 and 1. So this is an edge. We have 1 and 2. This is another edge. We have 2 and 3, another edge. And 3 and 0, another edge. And we have all the symmetries of this. So we have 1 and 0, 2 and 1, 3 and 2, and 0 and 3. Etc. So this is a small example of a graph, and this is the example that we'll have in mind throughout the lecture today. This is from general graph theory, but this is the only thing that we need to know before we come to see the paper. So even in the lecture notes, there are some preliminaries, and they state it over there, but this is at the end all the preliminaries we need to in order to come and understand the settings of the quantum walks in this regard, in this framework. So what we're going to cover is the lecture notes on quantum algorithm by Andrew Chaz, that he's going to give a guest lecture later on. So this is really nice. And we're going to focus on chapter 17, discrete time quantum walk. So the lecture notes are they accompany advanced course that he gave on quantum algorithms. So it's a graduate course, and he covers or review on the high level the sub-framework of quantum walk that we are going to cover now. And this is what we are going to follow. So we will take the lecture notes, the specific sub-chapter, and we'll map it into a concrete implementation. The only thing that we will cover is this. So it's quite short, but taking this and transforming it into actual code, actual quantum algorithm that runs, it's a bit tricky, and there are several nuances that we'll cover. But on the high level, only sub-chapter 17.1, discrete time quantum walk. And here, all the material that you need in order to understand the framework of quantum walk is here. And we are going to see how we map it into the concrete implementation. So we can see there are 4 high-level equations, even equation 17.1 we won't use. So we discuss 3 main equations, and also there are a lot of information is encoded within the paragraphs themselves. So now we will go step by step and understand how we can take this and transform it into a concrete implementation. The first thing, and this is not covered in the lecture notes, is that I highly recommend when you come to a new implementation or to a new quantum algorithm that you want to implement in practice, you should have a concrete example in mind. And it should be a simple or the simplest examples that demonstrate the key points of the algorithm. So this is a simple graph, a simple example. And actually, when I came to implement this specific algorithm, I started with a different example. And then I've seen that it's not the best example for this scenario. It wasn't the simplest, and it didn't cover all the cases. So sometimes you need to adapt and tweak the example that you work with throughout the implementation. But it's highly, highly recommended to have a concrete example when you try to understand the paper, the algorithm, even before you come to code it, actually to design it. Because also when you have like the high level notation or the high level mathematical framework, it's different when you are actually writing it by hand for the specific example you have. So if we go back, it's a different way to see here the bracket notation for the general case and to actually being able to write it for the specific example. It clarifies more the notation, the mathematical notation. So do keep in mind that you should have a simple concrete example throughout every paper implementation that you come to implement. Now, the first part is the encode. So we can see from the lines and the terminology used here. So he refers to an input state J corresponding to a vertex J in the set V. So what we understand from this, we understand that J encodes a vertex. So we have a quantum state. The quantum state represents a number or a superposition of numbers. So this can be up to normalization factor, a superposition of the node 0 and the node 1. So here in the text, it's written how we should encode our data, right? So we have vertices. This is a classical mathematical notation, vertices and sets. And now we encode it into quantum states. How we encode it? We have quantum states that are represented by numbers and superposition numbers. And for this, using the Classiq and the QMod language, we have QNum. So QNum is the variable that enables us to encode quantum states as numbers. And here we have just integer numbers. So we have a simple QNum. And how we code it, we have just the output vertices. So we have a quantum variable, which is type QNum, and we call this quantum variable vertices. So this is how we start. This is the encoding that we have. Quite straightforward, but again, it can be tricky to transform this line into a concrete implementation. So here we know that it's QNum because we have numbers that are part of the set. So the set that we have are the numbers 0, 1, 2, 3. So we want to encode them into a quantum state. We have the quantum variable vertices of type QNum. First step. But there is a caveat because later on in the paragraph, it's written that the Hilbert space consists of states of the form JK, where J and K are part of the set of the edges. So it's not as simple or as straightforward as we thought initially. Okay, but let's try to decompose it and understand what we need to do. So we have already the vertices. So we encoded it here. So we have another quantum variable that we need to encode as vertices. So K also encodes vertex or vertices in general. And there is a nuance that we need only connected vertices. So this becomes a bit trickier. So let's say, okay, we ignore it for now. We'll deal with it later. But on the high level, we know that we just need another quantum variable, another QNum that is called adjacent vertices. And this is all the adjacent vertices for a specific vertex. But how we only compose the specific connected edges, that we'll keep for later. So when we come to the implementation, we don't need to implement everything from scratch. We need to go through the paper that we've seen, the high-level framework. We should sketch the high-level pseudocode that we want to have. And then when we get into specific details that we have an intuition how to implement, but we are not sure now, and they are more complicated, we can leave it as, let's say, a black box for now, or just put or ignore them, or put like a dummy variable over there. And then later on, after we have the full picture, go back to the specific example. And when you're writing QMod, it's also very useful to use functions for each step that you have along the way. And then you don't need to fill the actual function when you code the entire thing. So it's quite useful to start from the high level scheme of the functions, and then after you have the full sketch of the algorithm, then to go into function, and then to go to the concrete implementation. So here we have the encoding first step, check. Now we can continue. So the second step is the evolution. And again, this is all the paper that we are going to deal with. And what we have for the evolution, we can see the definition of two operators. So here we have the operator C. Sometimes it's called also the W operator, and we have the operator S. So two kinds of operators, and we can see the summation indices in the bottom. And then it's written overall one step of the discrete quantum walk. One step of the discrete quantum walk is described by the unitary operator SC. So what we understand from this is that what we need to do is to implement the operator that is composed from S and C, and then we can iteratively apply it many times consecutively, and then we have our full quantum walk algorithm. We need to initialize also, but this is the heart of the evolution. So the evolution part of the quantum walk is to have these two operators applied. And on what they are applied on the states that we had in the first encoding. So maybe there will be additional step in the encoding. Maybe we'll put all the vertices in a superposition, but we know what's the encoding. We know what are the states that we are dealing with. They are encoded as quantum variables or as QNUMs. This is the type of the quantum variable that we encoded the data. And now the evolution, we know that we need to implement somehow these two operators. So we have S and C that we need to implement. Now let's start with the operator C. So what we see here, we see a summation over all the vertices in the set V, so over all the vertices that we have in our graph. And then we see that on the first QNUM, the first quantum variable, the first quantum register, so conditioned on the value of the first quantum variable or quantum register being J, we need to apply some operator that is of the form 2 times a projection operator of some state derivative J minus identity. Sounds complicated. Let's break it down step by step. First step, we have a summation J of all the vertices J in the graph that we have. So one way of doing it is doing an Hadamard transform over all the vertices. But another way of doing it, and maybe more appropriate for this example, is to do a repeat. So we want to repeat over all the vertices that we have. And here the index I represents what we have here as J. So we want to go over all the vertices that we have. So the vertices here, vertices is the QNUM that has or encodes all the vertices of the graph, and we want to iterate over all the vertices in the set V, so over all the vertices that we have. First step. Now the second step is this. I think we have a bit of a issue here. Okay, we'll get into it later. I think that there is missing a control part, but we'll go to it later. So let's continue with the second step. Here we see this operator, and the first equation or the second equation in the paper defines this operation. So this defines this state. So the definition of the state that we see here is to sum over for a specific index J is to an equal superposition of all the vertices that are connected to the vertex J. So for example, the state of derivative of 0 is a superposition of all the vertices that are connected to 0. So in our graph, it's a superposition of 3 and of 1. And we'll come to it later. But for now, ignore this part. So think that we have a unitary that creates this superposition for a given vertex, and assume we have access to this unitary. So we have the access to a unitary with subindex J that is action on the state 0, resulting in the desired state. So let's assume we have it, and also in the code we actually write it as we assume we have it, and we'll deal with it later. So it's not trivial how to implement it. So let's ignore it for now. Let's have the full high-level overview of the algorithm. Now, if we have the access to it, and again, we don't know how to implement it now, we'll deal with it later, but let's say we have and we know how to implement it, so we can decompose the operator here into uj and then 2 times projection on the 0 state minus the identity, and then the inverse of the unitary uj, right? So this is a simple trick that we use often, and now we can already see some patterns. So we have an operation uj, we do other operation or other unitary, the projection, and then we do the inverse of the unitary, and it should ring a bell of some concepts that we have within the QMod language, how we can encode this kind of operator into a specific quantum algorithm. So who is this projection operator minus 2 times projector minus the identity. Let's see a concrete example. So if we apply this operator on the state 0, so actually we stay in the state 0. So the state 0 is an eigenstate of this operator with an eigenvalue of 1. And also, if we apply it on any other integer state that is not 0, we receive, it's also an eigenstate, but with an eigenvalue of -1. So this is a simple mathematical derivation that we can come up with this. But this kind of operator is quite common, and I encourage you to think if you have seen it before, and the answer is that you've seen it, but in a moment we'll get into it. But try to just write it with a pen and paper and see that you receive the same result. And the results are that if we apply it on the state 0, we receive it's an eigenstate with the eigenvalue 1, and on any other integer state, it's an eigenstate with the eigenvalue -1. And this is exactly the phase kickback algorithm or phase kickback operator that we've seen and we've covered earlier. So if we apply it on a general state x, what we receive is the -1 to the power x doesn't equal 0 with the state, because it's an eigenstate, and this is the general eigenvalue. So let's see that we understand what's going here. So if we have the value of, let's say, x equal 1, so 1 does not equal 0, so the assignment of this is 1, so we receive a minus x. So that's good, or -1. And if it's 0, so the assignment is false, so it's 0, and then we receive the state 0 with an eigenvalue of 1. And this is exactly what we want to have. So this is the phase kickback, right? And now we actually see a quantum primitive that is hiding within the implementation of some advanced algorithm that we need to implement. And to be honest, when I came to the implementation of the quantum walk, I didn't know in advance that we'll have a phase kickback in it. But it's highly probable that when we come to and when we approach new quantum algorithms that we haven't implemented before, and there are advanced quantum algorithms, we'll encounter some of the quantum primitives that we covered in this part of the course, and additional quantum primitives, of course, because they are the tools, they are the building blocks for all these advanced quantum algorithms. So here, that's a nice example. We see how the phase kickback, the primitive that we learned in previous sessions and in the previous lecture, in the previous session, how this is being implemented or being used as part of this more complicated or more advanced quantum algorithm. So now there is a phase kickback. Now we know where we are in a safe place because we already implement the phase kickback. We know how to implement, so that's great. So let's implement it. So we have the phase kickback. We'll call it a zero diffuser, and this is used again in many applications in quantum computing, in quantum algorithms, so the zero diffuser. So we have a Q func we call zero diffuser, and it applies only on a QNum X. So to receive X, it initializes another auxiliary qubit for the phase kickback, and we use the within apply operation for the for actually applying the phase kickback. So within applying a prepare minus on the auxiliary qubit, we apply the oracle that we want to have, and this implements the phase kickback that we want to have for the X state. So that is very nice and very cool. But again, this is only a sub part within this operator seed that we are now trying to implement. So if we are going over the entire implementation, and here now we have the control, so we'll go over it more thoroughly. So first we have this summation, and the summation is done with the repeat. So we repeat over all the iteration of the vertices that we have. And for each iteration, for each summation, what we do, first we do a control. And this is the part that was missing from the previous slides. But what we have here is a projection on the state J. So effectively what it means only if the state is J, apply the corresponding operator. So the way we encode it in a quantum algorithm is that we use with QMod language, which captures really nice the operator that we see here, is we use the control construct. So what the code you see is from the native QMod syntax, but everything can be also written in Python. And at the end, I will give you the Python implementation of the entire quantum walk. And what we have here is the control, and it's conditioned on the fact that the vertices is I. So vertices is the quantum quantum variable, the QNUM, and only if the QNUM vertices equals I, we want to implement a specific quantum operator. So this is the second step. Now, what is the quantum operator that we want to apply once we have this control? We want to apply the decomposition of the operator 2 times the projection on this state minus identity into the unitary that prepares it and the zero diffuser, what we call the zero diffuser. So we use the within apply construct of QMod, and the first step is to do the within. So in place prepare desired state. So we didn't cover this function. So this is a new function. Now we just treat it as, let's say we have this function that prepares what we want to have. So it prepares the state uj that, so it implements the unitary uj, which what it does is given the zero state, it creates this state, the desired state. So here the implementation, we assume that now we have it, and we say, okay, if we have it, let's do a within apply. So this would be what we are doing in the parts of the within apply, in the sites. And then the action that of the within apply is to apply the zero diffuser. So this is the last part, the zero diffuser. And this is exactly what we want to implement with the C operator. So we almost have everything we need beside the last part, but this is the high level framework of how we implement this C operator. And I think now we can understand how the QMod language or the construct of the QMod language really capture core essence of quantum algorithms that we see in practice. So here it's an operator that we've written, or the author wrote on a pen and paper or in LaTeX, but we actually want to code it and to have a concrete implementation. And we cannot actually just copy and paste this line. We need to think in a smart way how we encode it. And this is how we do the encoding of each part of the operator. So the encoding may be used here in several terms, but this is how we let's say, transform an operator on paper into an actual operator that we implement using some quantum software. So this was the first operator, the C operator. How are we with time? Okay. So this was the first operator. Now we're going to the second operator, and the second operator is this S operator. So let's try to understand this operator. We see a summation over all the edges that we have in the graph. And over all the edges that we have in the graph, so all the tuples jk that are part of the set E, which represents all the edges that we have, we want to have a swap. So it's a swap conditioned if the two edges that we have, the two vertices that we have, actually have an edge connecting the two vertices. And if not, we don't want to do any swap or anything like this. So let's see how we encode it step by step. So again, now we need to think what does it mean to have this two vertices that are part of an edge. And this is exactly the use of an oracle. So we've covered an oracle in the phase kickback session, but we need to assume that we have some oracle, and we will build this oracle, or we will design the oracle, and we have a concrete implementation given by the synthesis engine. But we need somehow to design our oracle that will give us this condition that only the vertices that are part of our edges, or two vertices that contain an edge between them, are something that we want. So we have some indication, and what we will assume is that for our specific example here, we will sort of build this edge oracle. So before we go to the implementation, we see that the edge oracle will have a result. So we expect the result to be 1 if the specific value of the QNUM vertices and the specific value of the QNUM adjacent vertices are a part of our graph. So if we see that, for example, if we have the value of vertices is, or one component of the value of vertices is 0, and the other component is 1, so we want the qubit to be, the qubit res to be 1, because we have this edge. But if we'll have the value for vertices, or one of the components of vertices will be let's say 0, and for adjacent vertices will be 2. So we want the value of res to be 0 because there is no edge between 0 and 2. So this is by the definition and the use of Oracle, and now we can see it like in practice. So this is really nice. And Oracle we ask it a question. So are the value, or is the value of vertex and adjacent vertex is connected by an edge? And the result will be 1 if yes and 0 if no. Now, how we can encode it? So here we need to be a bit more sophisticated, maybe. So we can see that for this specific graph, so now it's only for this specific graph. It's the Oracle is really graph dependent. So for the specific example that we cover here for the specific graph, only if the sum of two vertices is odd, so we know they are connected by an edge. So let's try to understand it. If 0 and 1 are connected, so 0 plus 1 is 1, and then we see that the sum is odd, so we know that they are connected by a graph. And let's take the opposite example. We know that the vertices 1 and 3 are not connected, so the sum of 1 and 3 is 4, and it's not it's even, so we expect to receive the value 0. So this is a trick how to encode mathematically this specific graph that we have here. Now, because we are working with a specific example, we know to identify, or throughout the implementation, we identify what parts of the algorithm are general and what parts are very example specific. And the specific Oracle for, or the Oracle in general for as part of this algorithm must be a specific for a specific graph. So it's a graph dependent, but the structure here, it's the high level structure, right? So we have the qubit res and we have vertices and adjacent vertices. This structure is general for all the oracles that we have in this framework. And the fact that the qubit, the res, will be assigned the value 1 for if the value of vertices and adjacent vertices have an edge connecting them. So this is general for all the quantum walk implementations that we are going to have. It's only the specific graph that we encode in this way. And how we encode it, we have the value res, and we say that if the sum of vertices and adjacent vertices modulo 2 equals 1, so we want the assignment to be 1. So we have to have it, we want to have an assignment, and this encodes that only if the sum of two vertices is odd, so they have an edge. So this is a trick, or something that is not in the general case, how we actually encode it. But again, we could have written or gone through all the entire algorithm and just keep the function declaration, so edge oracle, and we know what we want to have the function. And then at the end, we would need to actually implement a specific oracle for this. And what we see here, it's okay, we need it as part of the S operator, so it's part of the evolution, but actually this is the encoding. So this is another part of how we encode the data into the algorithm. So the first encoding that we had is what the quantum states or the QNOMs are representing. Now, okay, so we encoded the set of vertices, but until now we didn't encode, or we haven't encoded the edges. And this is one way of how we encode the set of edges. And we encode it with this quantum oracle, or with this edge oracle. And we can view this as also as part of the evolution and as part of the encoding. So this is an interesting point that we encountered through the implementation of this quantum walks. Now we come to the full implementation of this S operator. So let's go step by step. So we have two QNOMs. So we have the vertices and we have the adjacent vertices. So we initialize another qubit, or we represent it as a QNOM here. And what we're doing is we apply this edge oracle. So the first thing that we want to do is to have to actually know for a specific component of vertices and the adjacent vertices if they are connected by an edge or not. And of course, everything that we are doing here is in a superposition. So this is we code our quantum algorithm in this way, but everything is applied in a superposition because we're dealing with the quantum algorithm. So this is super cool. So the first step is to declare a new qubit or a new QNAM that we'll use as the auxiliary. So this is the edge of the what we receive for the result of the edge oracle, and then conditioned, so control if the result or the value of res is 1. So it's conditioned only if the control res is 1. Do or apply a bitwise swap between the vertices and the adjacent vertices. So this is what we apply in here. So here we don't go over all the edges. We say that we build our S operator in a way that we receive some vertex. We don't know if it's in a superposition, if it's covers all the vertices, but we assume when we build it, and this is a design choice that we've done throughout the implementation. But for the scope of this, we say the S operator received the vertices. We don't go through the entire set of vertices as we did with the C operator, and condition that for the specific value of vertices the adjacent vertices, we have a connected edge between them. So we want to apply the bitwise swap. And this is how we encode or code this S operator into this specific, the concrete implementation with the cumulative. So what we have so far. So we have this example that we are going through now. So this is our graph. And we didn't cover it, but we need a way to initialize our quantum variable. So in our example, we initialize, so we allocate 2 qubits for vertices. So we have 4 possible values, so we need 2 qubits. And just for the sake of having a superposition and doing everything in parallel, so we initialize with the Hadamard transform. It's not part of the general implementation that we want to have, but we want to work with this specific example, so we need to also initialize for a concrete initialization. So we choose to initialize in the Hadamard transform, and now the first part, it will be dependent on the specific quantum walk algorithm that you are going to implement. But again, we are trying to implement a specific example that will be as general as possible. So this is the more specific part. So we initialize vertices. We apply a Hadamard transform on it just to have a superposition of all possible vertices. We initialize also the adjacent vertices. We apply the W operator, and it applies on the vertices and adjacent vertices. We apply the S operator, and this is our quantum walk algorithm or quantum walk operator. What is the S operator? This is what we covered now. What is the W operator? This is what we covered earlier. So very elegant and very, we had to go through several nuances and several caveats when we came from reading the paper to actually implementing it. And we didn't finish, right? So we have one thing that we left for the end, but this is what we have so far on the very high level. This is quite nice, and I think quite intuitive compared to this kind of advanced framework, but this is how we move from paper and reading and about the quantum algorithm to actually implementing it in practice. Now let's dive into the missing part. So we have this C operator, and we have the quantum state that is defined here. So it's part of the C operator. And we said earlier that we want to have just a unitary that prepares this state for us. Now let's try to understand it a bit more. So this state, what it means for a specific value of J, so for a specific state that we have, we want to have an equal superposition. So the degree of J is how many connected vertices the specific vertex J has. So we want to have an equal superposition of all the adjacent vertices that are adjacent to the vertex we have. So here we have an example for the state 0 in our example. We want to have a probability vector that is an equal superposition of vertices 3 and 1, because these are the adjacent vertices that we have. And for state 1, so this is on the right, we want to have an equal superposition of the vertices 0 and 2, and so on and so forth. So, okay, we go through the concrete example. Let's try to understand how we can actually implement it. And then we see that we need to initialize some probability prob array, so it encodes our probabilities. And then we see that we have this I plus 1. So for a given, so here you should think about I as j. So for a given j, so we want to have j plus 1 modulo 4. So we want to have, this is one state that we have, and j minus 1 modulo 4, this is the other state that we have. And this generates the desired probability vector that we have. And once we have the probability vector, we can actually implement it with the in-place per state function that was by Classiq. So the in-place per state actually prepares the state according to what we want. So the probabilities of the in-place per state would be just the prob array. Bound is just how close to the actual value of the probability we want to implement it. So this is a design option. And the target, so what we apply it on, so on what state, we want to apply it on the adjacent vertices. And here, as you can see, or you will see later, this is something that we had to move to Python SDK for this, because here we use some classical logic and we use this Python framework in order to have this kind of slicing and choosing the specific values. So at the moment, you cannot implement this specific part in the native QMod syntax. So you can leave it as is and go to the Python implementation. Hopefully in the coming weeks, we'll be able to release a version that actually empower you with the abilities to code it also in the native QMod syntax. And this is now a work in progress, so stay tuned for this. But with the Python SDK combined with the Classiq package, you can do everything. And in the code that you receive, so I will give you the code, the algorithm, the implementation of the algorithm as part of the homework assignment, and then we'll go over the implementation and you will see how to incorporate, how to use sometimes the Python capabilities, Python arithmetic, and sometimes how to use this QMod arithmetics. So going back to the implementation, we have this probability vector that we want to have. We implement it by an in-place per state. And again, this is the operation that we want to have. So let's go back to the implementation. We see that we have a unitary. So the unitary is the in-place per state, and we applied, we sandwich between this unitary, this projection, 2 times projection on the 0 state minus 1. And now we can see that the full implementation of this part is controlled if the vertices is equal I. What we want to do, we want to have the within apply. So within apply actually enable us to do this sandwich, to do this basis transformation, to apply in the basis that we move after the application of the unitary uj. We want to apply this operator, this 2 times projection minus identity, and then to go back to the original basis. So this is the within apply construct, and within apply, we first compute, or we move to the new basis of the in-place per state. This is the unitary j. We apply the 0 diffuser, so this is this part, and then we apply the within apply, automatically applies the unitary j intus, the unitary j dagger. So, and now we can see how we actually implement it in practice. And again, here, this is, as we covered earlier with the S operator, the summation over the specific edges. Here we can see that this state or this operator also encodes some data about our problem. So this is a part of the evolution, of course, but this also encodes part of the data that we have. And there are further ways and further tricks to how to implement it efficiently in the more general case. This is, again, a concrete example. We want to walk through it, and we just want to have some implementation to have a full example. Of course, or not of course, but usually the first implementation that we will come up with when you implement the paper won't be the most optimal implementation, the most efficient one, but it's good. We need to start with implementation that works, and then after we have this full implementation that actually works for a specific concrete example, we can continue and evolve our algorithm and to make it more efficient in iterations. But this going from 0 to 1, so from having no implementation to some implementation to an implementation, this is the hardest part. Once we have the implementation, to make it better and better and more efficient, that's sometimes also hard, and there are some leaps that sometimes should be overcome, but actually encoding it for the first time, having it working, this is, I think, the hardest part. And once you overcome this, it will be easier and easier to optimize your algorithm. Okay, so having everything together, so in the canvas you'll have link for everything, but you have the full implementation that I went through today in the Classiq Git library. So the Classiq library, community, and then the Womanium folder assignments, and within the assignment you have the Python. It's not the Jupyter notebook, it's just the Python code that contains the implementation of the specific algorithm that we had today. Let's see the actual circuit for this implementation. So now I'm here in the platform, and here we can see the actual implementation that I received. So let me try to make it as large as possible. So first we can see some parameters, some details about the quantum program that we received and the transpiled circuit. So we see the transpiled circuit has a depth of 63 and it uses 8 qubits, so it's quite a small circuit. We have a small example and we did only the one iteration. We just wanted to have this quantum walk operator at hand. So this is just to have a feeling of what we are dealing with. So this is the size. Now this is the actual quantum program that we received out of the design of the algorithm. So first we can see the Hadamard transform, and we can see here the two QNAMs. So we have vertices and we have the adjacent vertices. So we apply the Hadamard transform on the vertices. Again, this is just how we wanted to implement this specific example. Now we see the W operator and the S operator, and you should think about the W operator as the C operator. And when you implement the homework assignment, so you can change also the names. And usually the W operator refers to C and S applied consecutively. So let me even change it here. So this is the C operator. Now, let's see, let's start with the S operator. So we see that we have this edge oracle that identifies if we have an edge or not. So it receives vertices, it receives adjacent vertices, and the result is 1 if the vertices, the value of the QNAM vertices and the value of the QNAM adjacent vertices is connected by an edge for the specific graph that we encoded. And if it's connected by an edge, apply a bitwise swap. So here we can see a controlled bitwise swap. So this is composed out of 2 building blocks, quite intuitive and a very nice implementation and use of what is an oracle, right? So we often speak about oracle. We've seen some implementation or some use of the oracle in the phase kickback, but it was, again, the use for some quantum primitive. Here we see about for a general quantum framework, the quantum walk framework, we see how we use actually in practice in a maybe non-trivial way, a quantum oracle. So this is very nice. S operator, the C operator, we can see we have 4 iterations. So we have, let's try to understand it on the more, let's try to understand it on a more high level. So we see here 1 repetition of something. We see here the second repetition. We see here the third repetition. I think this is not the most updated code. We should have also the 4th repetition. But when you run the code, you will receive the 4th repetition as well. So we see that conditioned on specific value, we apply the 0 diffuser. We would also expect to have conditioned also on this value to apply this state preparation and state preparation inverse. Apparently, the synthesis engine, the compiler, chooses not to do it in this way, probably because it's not the most efficient way. So apparently, if we would have here the control with the same value and control here with the same value, it will result in the same result as we have in this quantum program that we view. So with the state preparation, the 0 diffuser, and the state preparation inverse, let's try to think about it. If the value is not assigned, so the control will not apply, and then state preparation and state preparation inverse will be just the identity, and we don't apply anything. So this is a smart decision that we can see the compiler, the synthesis engine of Classiq, apply, because we didn't tell it ignore the control states of the state preparation at the beginning and at the end. If I'm going back to the implementation, what we view here is the W operator, or we change the name C. It's the control that the vertices equals I, apply the within apply of the in place desired state and the zero diffuser. So we see that the control applied on both parts of this operator, but here the control, the implementation only on the main part. So this is a nice way to view it. And you can zoom in into the specific implementations and understand them more thoroughly. But this is also the W operator, or the C operator, to pronounce it in a better way. And that's it. So I think if we go back, I think now that we covered from the paper, reading through the paper together, identifying what the meaning of the equations and what is the meaning of the paragraphs in between, and where the data is hiding within this paper, how we encode the data, how we evolve the data, how we work with a specific example in mind. I think now I hope that it gives you more confidence in approaching the implementation of advanced quantum algorithms. And I really hope that you took from this the way of thinking, how you should approach to coming and implementing a new quantum algorithm that you see, how you decompose it into the states, how you decompose it into the encoding part and the evolution part, and that you have the specific example in mind. And it should be a simple example, but not simple, or simple, but that reflects on the general case as much as possible. And then you can adapt the example throughout if you understand in a better way what the example should be. And then how to, as part of the evolution part, to encode further data into the algorithm. Okay, so further reading about the quantum walks in general. So there's this review on quantum walk computing, theory, implementation, application. This is a more high-level review that can cover all the different aspects that the quantum walks have. So continuous time quantum walks and discrete time quantum walks. And within the discrete time quantum walk, there are several frameworks. So there is the original proposal for quantum walks, and then there is a new proposal that is more efficient or more applicable for more cases or for some cases. So I encourage you to go over it and maybe to skim through, and then to have the high-level understanding of what are quantum walks. And this is a specific application of quantum walks, so quantum walk speed up for backtracking algorithms, and by Ashley Montanera. And I encourage you also to skim through the paper. This is an application of quantum walk for backtracking algorithm, and over there he covers again how to adapt this framework of quantum walks into the specific application. And now when you approach this kind of paper, so this is not part of the 3 papers that you should implement as part of the Classiq project, but if you want to do an extra project or for yourself, I think it's also interesting to try to go and implement this quantum walk speed up of backtracking algorithm. And over there, when you will go to and try to implement it, you have different nuances that you need to overcome, and how you encode the data, and how you evolve the data in a smart way, how you encode your oracles. So there are many nuances that you need to come up in a smart way, and maybe to bring some novelty to the kind of implementation. But I encourage you to go through both these papers. So one is a more review paper, one is a more concrete example of an algorithm that uses quantum walk. So just before we continue, and this is a build-up also for the next part. So the final assignment, you have it in Canvas, and you have it also in the Git library. So as part of the community Womanium assignment, you can view over there the final assignment. And the assignment on the high level is to implement the same algorithm, and you have the implementation of the example we covered here for this kind of graph. So it's not the circle graph that we've covered. This is a different kind of graph, and you need to come up with your own encoding of the data, of the operator, of the oracles, and you need to request for the Classiq Git library. And that is a good ending for this part, because this is exactly the things that Amir are going to discuss now.
Wonderful. Thanks a lot, Eden. And next up, we have Amir Nawef from Classiq. Amir, would you like to give a quick introduction of yourself, and then the stage is all yours?
Yeah, thank you. I'm sorry I couldn't join from the beginning, but it looks like really good turnout and really good content so far. And I see Marlu here, and I guess a few others that I already know. So hi everyone. Thank you for joining Womanium in general, and these sessions in particular. My name is Amir Naveh. I'm one of the co-founders of Classiq and leading the algorithms team. Yeah, I think this is a really good opportunity for us to present Classiq and quantum algorithm design in general, and I think a really good opportunity for everyone to kind of learn, but also to experiment. Yeah, congratulations for everyone who is joining and participating. Maybe I will briefly share something that I am personally passionate about, and then also I won't be long, so I know we have around 15 minutes, but I will try to take less than 10 and also leave some time if people want to have any questions or comments. So I know a lot of you are not with your shared screen, but I would like it actually to be interactive. So as much as any of you can, if you could just kind of follow me on what I'm doing now and kind of actively engage, that would be, I think, the most helpful. So let me share my screen. Maybe let's open a new tab for it. Okay, so hopefully all of you are aware of the Classiq library. So go to Google, search Classiq library, or go to just the specific domain and open this so that kind of it's in front of you, and I'll give you kind of a guided tour of our Classiq library and how you should use it in order to both learn and to experience hand-on in quantum algorithm development. So I'll give everyone just a couple of seconds here to get it on your screen as well, and make the engagement more interactive. Okay, so this is something that I'm personally very passionate about. Classiq, as you know, is building what is needed in order to create algorithms and applications. But as part of what we learned, then having examples for everything and actually developing them helps people to start out. So we've put everything here in this GitHub repository, and everything here is open source. So to access this, you don't need any permissions. You can do anything you want with these files. I want to walk through with you on a few things. First, and of course, this is optional, but it would be really nice for Classiq, and I think also for you, if you could start the repository and watch it, and in general, pin it to your personal kind of workspace. This makes it visible for you when you are accessing GitHub, and it also actually helps the community in kind of saying, here is a trusted resource that you are kind of people have voted on it. So this is quite nice. So if you could do it now or later, it would be really, really helpful. And then a few things that I would show. I will first show you how the resources are organized, and then I will show you how to contribute something if you want and kind of want to work hands-on. So there are a few directories here which are most important. Let's start maybe with algorithms. So in this algorithms directory, you have most of the basic common algorithms that you've probably heard of, right? From basic ones like Simon's algorithm or Bernstein-Vazirani, to things that are more complicated like the HHL algorithm. And then just for example, we can open the HHL directory, and for each you will have the following. You will have a Python notebook, and if you press it in the GitHub, you can see that it's giving you like a full walkthrough of how it's working, right? So it's not just like the code, it's also an explanation. It has references. And also you can run this notebook completely on your own. All you need is kind of to do pip install Classiq before this. So to be honest, I don't know of any other real implementation for the HHL algorithm. It's quite a useful one. And there are almost all the algorithms you can think of are in this directory. So kind of, if you're just interested in something or want to learn, I think this is an excellent resource. Also in the directory, you will have the QMod file, right? So this you can upload directly into the IDE, and it will be a working representation of this of the quantum model, and they are essentially equivalent. So this QMod, it's generated automatically. At some point in the notebook, you will notice that there is a line called write QMod, right? Usually after we synthesize the model, right? So here we can have create model, and you see here write QMod. So this automatically generates the quantum model from the Python code. So it's just equivalent. So this is kind of a really good way to learn about algorithms. Second, I would recommend that you also look at the applications folder. Here you have things that are more like for specific problems. So for example, if you go into optimization, you can see all these like optimization problems, knapsack or max click or max cut or dominating set. These are all like really well-known optimization problems, and you can see how they are implemented. So now you have a new optimization problem. Once you go through 2 or 3 of these, it's very easy to figure out how to do your own. So this is also an interesting directory. And then finally, what I wanted to show, so, okay, once you've explored this and you looked at some of the algorithms and you've kind of got yourself a bit more you're a bit more aware of what's happening. So we really welcome you to contribute. So what you do to contribute, you go into issues here. You can see that there are quite a lot of open issues. Most of these are opened by our team. So if you see like quantum expert, for example, or quantum intermediate, this is the level that we would expect someone to tackle it, right? So for example, here, this issue is implementing the partition functions, and it's also connected to the quantum algorithm zoo. So if you implement this one, then it will be connected to the quantum algorithm zoo, which is quite like a very well-known kind of aggregation of many quantum algorithms as well. So it has Classiq implementations are also kind of directed from the quantum algorithm zoo. But also, let's say you have a new optimization problem or a new paper that you want to write or anything like this. So you just open a new issue, you press on this green button here, and you tell us what you want to do. And our team is very responsive. We will look at this once a day or once every 2 days and respond, tell you, okay, this sounds interesting. Here is how you would work on it. Here is what we would recommend, help you out in implementing. So it's not just that you will be implementing it, you will also get like really close support. And in the end, you are contributing to kind of this open source library, and everyone can later access what you've done. You can see that we have quite a lot of contributors already. So 44 people have already contributed to this library. So most of these are not from Classiq, they are external contributors. So you're really welcome to be one of them. This is part of the advantages of being an open source in this sense that kind of we view application and algorithm development as something that is very well handled by the community. Think of it kind of like a quantum application store. So if you create something new, it's really nice if you put it here, and you will get the credit for it, etc. Yeah, that's it. It's I think it's a really nice way if you're learning, if you think, okay, I want to get into quantum or I want to implement something, how do I do it in practice? I think this is a really good resource. And also once it's here, it will stay valid forever. So every time we do a version update, for example, we take everything in this directory and we make sure it's working with the updated syntax and with the updated APIs, etc. So it's kind of like you submit this once, and then you are sure that it's a part of the community forever. yeah, I think this is what I wanted to share with you. And I'd be really happy to answer anything now or offline at any point that people would like to ask.
Thanks a lot, Amir, for a lovely session and actually guiding all the participants through your GitHub repository. So I think it's a very good session, and the participants can learn how they can start contributing immediately to the Classiq GitHub.